Okay. Hello, everybody. Welcome to lecture number 8, where we bravely carry on through our phenomenological observations. So last time we talked about very important phenomena, quantum interference, and we analyze it from the perspective of measurements, specifically coarse-grained measurements. That was the key invention here, right? And we conclusion from our analysis was that the interference, it occurs, but in a special way. But in quantum mechanics, it occurs pairwise. It's a pairwise interference, right? And then, like to this particular feature, we were able to like summarize succinctly with this parametrization we introduced, formal parametrization of where we introduced the functions so introduced functions I, F, so the same set of indices that are functions of pairs of sequences. The real numbers, so not necessarily positive. And those functions, we defined for them some properties. So instead of writing everything down, Emilia, you haven't seen this. It was the second part. So we demanded a couple of things from those functions, that the diagonal part is, the probabilities are parameterized as a diagonal part. Those functions are symmetric with respect to flipping their sequences, their arguments, and that they exhibit this funny property that if you treat coarse graining, this V, as a like formal operation on sequences, then those I's, they exhibit additivity. So they allow you, so this parameterization allow you to reduce coarse graining into fine graining, okay? And so, yes, so if you take this, take those functions I, use those properties, we define them, then you take a probability that involves coarse-grained measurements, so those that involve quantum interference, right? Describe quantum interference, then you can nicely like decompose everything into a combination of those functions I. And this pairwise interference is encoded in those I's because they are pairwise translates directly into the I's being functions of two sequences. Okay, if interference were three-way or four-way, quadruple-wise or quartet-wise, no? That would mean then I would have to have 4 arguments, and five-way 5 arguments, and so on and so forth. So this is like, nicely summarizes what's going on. Yes, go ahead.
I just have one final question for this two trajectories interference. But, all other statements that you made were kind of intuitive for us, or at least for me, or such a one that I know from a basic or a standard quantum mechanics course, that you have this causality, you have those other things. But the thing that there's always just two trajectories, I haven't really seen it before looking on standard quantum mechanics, that you always interfere one-to-one, yeah, that it's never more. And is there like a very simple convincing argument on a simple, let's say, system, I don't know, 2 qubits or something?
If you want to like
then we see that definitely there is only 2, never 3.
Equation-wise, let's say, if you want like simple like mathematical reason why there are 2 or not more. So this is actually Mariusz brought it up last time. so he said that, oh, okay, so if you want to calculate a probability, so you take you take the probability amplitude, one sequence, probability amplitude, and you square it, okay? And so if there was more, if you not square, but to the higher power, you would have that would reflect the fact that there is let's say four-way interference rather than two-way.
That's actually very deep. When I was a very beginning student, even I think in a high school, and I heard that they are wave functions and the probability is a square of wave function. I was like, what is stupidity? Why they couldn't operate already on those wave functions on those squares instead of wave functions? So we claim that, and now I see it may be better that indeed the fact that it is squared, it makes it. It is this interference. Without it, we wouldn't have any interference. Okay.
Yeah, although be careful with correlations, not causation, right? It's not like there is a pairwise interference because you take square. It's rather you take square because like fundamentally quantum mechanics is pairwise.
It's just how we see it. We see it because we take squares.
In standard formalism, you take square, okay? But you can have different formalism, right? But the fact that there are pairwise interference has to be reflected. If your formalism is any good, it has to kind of build around this fact, because this is like the fundamental thing. I think. I mean, it is fundamental. This is what ultimately will lock in what kind of formalism has to be implemented. This feature, okay, this particular feature. The rest are details. Although we go to the next bit, because we are not done with interference. Okay, because this parameterization with I, it like nicely solves for us the issue of describing this coarse-grained measurements which lead to interference. However, as it turns out, it does not, I is not sufficient to describe all interference experiments you can come up with. And I is completely fine if you are dealing with coarse-grained measurements on a single system. But if you introduce a concept that you can have two systems and you doing a big experiment on both of them at the same time, there is a new kind of interference that comes up, and just I is insufficient. You have to extend it a bit to get a real description. So we want to suss out what's going on here. So idea is to have a system that can be split into subsystems, right? And this is an intuitive thing, right? We feel it. We know what's going on. However, we are playing the game of phenomenological physics here. So we have to start with defining a system that can be partitioned into subsystem, but in a phenomenological way. So we want to define partitionable system like that in terms of measurements only. Okay, it's a fun exercise to try to do it, and I really want to share it with you because I'm very proud of it. Nobody in the beginning we weren't sure if this is actually worth the hassle, but I just felt that I have to try, and beautiful discussion ensued then, and I just want to share with you those beautiful discussions. So we formulated this definition of the composite system, and I will write it down here for you, okay? So let's call it phenomenological definition of, let's say, a composite system. But we know what we're talking about, although I won't be using the word composite in this. And I will explain the reasons soon. Okay, so here goes the definition. A system will be said to be partitionable into subsystems. A system will be said to be difficult word, partitionable into subsystems, when it is possible to deploy, when it is possible to deploy at the same time, the distinct measuring devices that could also be deployed individually, could also be deployed individually. To measure the corresponding observables one at a time. The corresponding observables, less one at the time. If this is the case, then each of those observables, each of those observables can be attributed to one of the subsystems, to one of the subsystems. The system is partitionable into. With a mouth. So the idea is that you have your system, and you have two devices. One device measures observable A, one observable B. And you can deploy those devices individually, okay? But you can also deploy them in tandem at the same time, okay? If you can do this, then you can like attribute A to subsystem A, B to subsystem B.
But A and B can measure properties of the whole system. Yeah, at once.
Yeah.
So now the partition will be the partition.
Yeah.
Just imagine that I have something that two devices are close
Yeah.
together, but they both can measure the whole system. Then it is partitions, partitions or not.
Yeah, if you can deploy it at the same time, if it's even possible to do it, okay. Because there are. I have some, because this definition sounds like I give it to you, right? But there is what you have in your head. How you know your quantum mechanics, standard quantum mechanics. You know what partitionable or composite system is. So there are immediately you are seeing some holes in this, and so I have prepared. I have prepared comments, okay, which are designed to answer those questions. Okay?
Partition means that they are like this. I have a system, and for example, I divided it. It doesn't have to be a wall, but I say that some part of the system is
Okay.
part A, another part of the system is part B. It can be some communication, it can be some interaction, but
Let's start with the cartoonish, very silly example where you have one laboratory on the moon, the other on the moon of Saturn or something. They never communicate with each other. But you can, but this is those two laboratories is my system, right? Well, something in the laboratories is my system. It's my system. Okay. And now I can do measurements in laboratory on Earth's moon, and I can do measurements with different device in Saturn. I mean, I have device on Saturn. I have device on the moon. Okay. A system. I do those measurements. Okay, and I can do them at the same time. Okay. I can do it. Nothing stops me. It's doable. It's physically doable for me. So now I can say, okay, in that case, this allows me to say, okay, so my system, that's laboratory on the moon and laboratory on Saturn, is actually partitionable into two subsystems, one on Saturn, one on the moon. And I know that because I did my measurements. I can do measurements here. I can do measurements here, and I can do them at the same time. Okay. So this is what allows me to do this. And now you can also go to, let's say, in one laboratory. Okay, and you have your devices, which are, those devices are physical objects, right? They have some bulk. They take some space, right? So I have device that I can deploy to my system, and I do measurements, A device, and I have B device, which I can also deploy individually to my system. And now the question is, can I do it both at the same time? Remembering that, those devices are physical objects, independent constructs, because, if they weren't, I couldn't deploy them individually. And now my requirement to even consider that there is, idea to think of my system as composed of a couple parts, that I can I deploy those two devices at the same time? Okay. This is what prompts me to even consider that there is a reason to to partition system into bits.
But having two devices which can measure at once the same system, how it is connected to partitions? I can have two devices at the moment.
Yeah, I also slightly don't see
two eyes, and I can look at the same time at the object. So where is the concept of partition system into subsystems?
Why? Okay.
With my education in the sense of having the knowledge of quantum mechanics already, I would say that it is when I can divide the Hilbert space into some whatever product of Hilbert or some other Hilbert spaces.
Yeah,
It's
that's
not
true.
necessarily that you can do different divisions for a system. For example, already for two qubits, you can divide it in different ways, but into two or orthogonal. So,
Yeah.
so actually,
You know-
there is an important thing which I don't see in your description, that this partition, these two partitions, they, although they could interact with each other, they do not overlap in terms of the vector in this subsystem is only in this subsystem, and there is some orthogonal subsystem, yeah, in the sense that it is orthogonal by partitions in it.
I will make you a caveat, because if you think about it, if you cannot rely on, okay, Hilbert spaces, we don't have those yet, and in specifically that outer product of Hilbert spaces, we cannot rely on that either, right? The only thing you can do is measurements, right? Now, in those confines, these are our constraints. Try to figure out how to define partitionable system, okay? And now, I gave you this definition.
The same, can have those devices.
Okay, I gave you this definition, and I'm not claiming here that it will completely 100% overlap with definition you would use in standard formalism. That this captures all possible, divisions into.
Sure. So,
However, what it gives me, a good definition from this. It's the follow-up definition of independent subsystems. If you want to have independent subsystems, first you have to be able to talk about subsystems, right? First you have partitions, then you can speak if those partitions are independent of each other. This independent subsystems that I get from this definition, it's the same as I would, in the standard notion. And this is what I care about here, okay? So even if this play with devices doesn't capture all cases, or maybe over captures some cases that are, it's not exactly the same as the standard Hilbert space definition, okay? We can take it, okay? It's okay. Yes.
So for example, let us have two eyes and one object.
Two eyes and one object.
And both eyes can see a whole object.
Okay.
Is there, yes, yeah, with some another.
Okay.
Is there partition or not?
Well, I guess what you would actually eyes. Okay. So,
or I need to somehow limit the possibility of my eye to see only a part of the object.
I would say, I think that the better, I mean, the fact that their eye is a device that takes room and so forth, it's important, but you cannot. I think it's important to also remember that those devices measure something, some observable. Okay, so. Are those two eyes of yours, are they measuring different observables or not? This would be key. If they measure this, if they measure the same observable, there is no difference between them essentially, right?
The same. I mean, eye is a very good example because it's like a projector. It projects the object to some play, yeah?
And
ultimately it doesn't, right? It's
to the states, the two compatible systems, English state, you measure the GH interaction in both sides. So if you have actually hard to see everything, so you have to actually state or single state. But both sides actually cannot recognize it is single state due to single measurement. But if you repeat measurement, so you can see actually both actually parts entangled.
But it's not okay. We are not we are not talking here about tomography of states and stuff like that. It's just you singlet. I mean, the system made out of 2 qubits. I would say it's partitionable if you can do measurement on 1 qubit, and there is another device that can do measurement on the other qubit. Right?
Only.
I mean, you can have device that measures both of them at the same time, but
But then
if you have a pair of devices that could be like arranged this way, that you can, for example, then it would give you a reason to, you would say that you have partitionable system. In this case, because of qubits, but even okay, but I'm not, I don't have quantum states even. I just want to have partitionable systems. I'm not.
You are partition anything like quantum mechanics, you can take any basis, even you can take a singular basis to describe body system. So it's completely arbitrary, but in our intuition, you always try to distinguish one system or another by particle or something else. You don't actually describe one particle with 2 composite systems. You always try to describe one particle in one single state.
Look, we're not talking about states. We're just talking about, can you, because look, if you don't have something like described in this definition, there is no, you don't have those devices that can be deployed in tandem, right? You have your set of devices, you deploy them one at a time, and you have your measurements, right? What is the reason to even consider that there are parts of your system?
Yeah, so that's
description of the quantum mechanics description. If you only measure independently, you cannot actually make the full system. You cannot describe the system.
The only thing we get is students made some measurements in a basement. We don't know that there are states, quantum mechanics. We are uncovering stuff. And now I want to distinguish 2 scenarios. One when you have your devices, you can deploy them one at a time, but it's like there's no, you cannot fit them to do the measurement at the same time. Let's say they are just too bulky or something. Your system is too small. I don't know, whatever. And in that case, you have no reason to even consider that your system has some parts that you could partition into. There's just no reason to think that. So what would be a scenario where you would get such a reason? And this definition defines such a scenario, right?
Yes, but in this definition, you say the system will be said to be partial when it is possible to deploy at the same time the distinct measuring devices.
Yes, distinct. This is important. The distinct devices that could be also deployed one at a time.
Devices see the whole object. So then why you say
that's okay? I don't know how they work microscopically. We don't know. We don't have theory yet.
Because partition in somehow my sense of understanding is that I have an object. I divide it somehow by 2. It doesn't have to be a 1. I want to say that left part from the 0 is a 1 partition, and right hand part is the left.
Okay.
But then you want to say that you could have the 2 devices which measure the object, the whole object. So why there should be a partition?
Why do you just interrogate your intuition here? Okay, you're saying that you have your system is just from this is first part, this is second part. how do you have this picture that it's like spatially distributed?
Something, yes, I don't know.
How do you know? You have to, there's some device would have to tell you that. For example, you have a device that can be that deployed here, right? And it clicks, does something. You have the other device that can be deployed here, and it also clicks.
So you,
But and now because you can deploy them at the same time, they both do their thing. But you can also deploy them one at a time. Oh, so probably my system is like spatially, it has some spatial distribution, and this part here, this part here.
don't assume any knowledge about
Yes,
object.
yes. This is our we only have those probabilities, and we only have devices which we don't have microscopic theory for them. Yes, exactly. That's what it's phenomenological definition, right? So that's why it's super interesting exercise, right? Once you start to realize how little you have.
So even they can be applied at once.
Given that they are devices, they take some space.
Yes,
right?
Maybe some output of this measurement.
But it tells us something about the observables that we measure with those devices. Something like, I wouldn't say that already that they are commuting, but
Oh, commuting. This is good, because this is one of the things that because measuring at the same time, this seems to like this is like commute. You can measure. Standard quantum mechanics tells us that commuting observables can be measured at the same time, right? So how does it? So is this definition?
measure at the same time, but without interruption one by another. But here, I'm not saying if the one measure will affect the other, but I measure two.
Affecting. Hubert, I already criticized the idea of invasiveness. It's a just abandon this idea. But the thing that you can standard textbook tells you commuting observables represented by commuting operators, which we don't have this yet, right? We'll get to this, but we don't have it yet. Can be measured at the same time, right? And I'm talking here about deploying measuring devices at the same time. Is this like conflict here? Is it like, and the answer is that specific answer to commuting observables, because this is one of the things that everyone is like has objection to. It's like in standard formalism, right? Measuring device is characterized by partitioning of Hilbert space into some images of projection operators, essentially, right? Commuting observables are represented by operators which have the same eigenspaces, right? Right, commuting observables have maybe they can have different eigenvalues, but they have the same eigenspaces. So if your device is represented by a partitioning of the Hilbert space into those subspaces, and your commuting observables are also defined by the some partitioning into eigenspaces, then the device, you deploy a device characterized by some set of projection operators, it then measures all commuting observables at the same time. Okay, this is what it tells you. Because right, standard quantum mechanics talks about not measurements are not about observables, they're about projections onto some parts of Hilbert space. Commuting observables have the same, this are compatible with the same set of projection operators, right? Therefore, measurement with device is it measures all commuting observables at the same time. Okay, this is what standard quantum mechanics tells us. So now, but in this sense of our definition, so you have device that measures all commuting observables at the same time, but you want to have you want to deploy another copy of the device at the same time. Okay, but if it's a copy of the same device, then it's in the same space. You cannot do this. All right. So there is commuting observables are in this sense trivial. You might say that, okay, I can like defeat this issue by augmenting my devices with some mechanism that splits the system and just diverts it, right? So I have room for my devices, copies of devices, right? But then I would say, okay, if you can split and divert your system into parts, well, it's partitionable, so it's okay, it's good, right? So I don't know if this explains this, but it's really fun intellectual exercise here to figure this out, right? How little you have if you cannot rely on your wave functions and stuff like that. Only devices which you don't even specify how they work. This is
So in this
quite
case,
cool. Distinct, yeah, distinct in the sense that they are, physical object number one, physical object number two. So
they measure on the same basis.
whatever. I don't know. It tells me I have my device and I can deploy it, and there is another device that can also be deployed. I don't know. I don't have basis here right now. Okay. We don't have Hilbert spaces here. But it's key that they are physical objects, right? Because then deploying them at the same time requires some kind of, that you have to be able to do something with your system, essentially. Although if one device measures like position and the other's the spin, and they can be like, deployed at the same time, because they probably could be, right? That would, again, be, according to this definition, you could then partition your system into like position degrees of freedom and spin degrees of freedom, which is okay. By all means, that's okay. So it's a fun thing to think about. Okay. And again, if some standard notion of composite system, that's why I'm using partition but not composite here. Okay, because I cannot prove that they are completely standard notion in the sense of product of Hilbert spaces. It's like completely, captured by this definition here, but it might not, but it's not an issue here because now we want partitionable to say that there is a special case when your system is partitionable into independent subsystems, and the independent subsystems, that's all fine. Okay, it's with standard notions also captured here. So we can talk about it later if you. This is very cool. I mean, we with Łukasz, Fata, and Darek, Davide, we just discuss it for many hours. This two sentences. It was so much fun. Okay, so all right. So imagine now that we have a experimenter got their hands on a system that is partitionable, and we have A device and B device. Those devices, these are those devices that define this partition for us. Okay. So we have a partitionable system, partitionable system. system. And we have, we can call it, so we have A subsystem, A and B subsystems, okay? Subsystems.
Actually, this A and B are the observables we can measure in this.
Yes, so yeah, just to make notation more succinct, the devices with respect to which we do this partitioning, let's call them A and B as well. So this will correspond to A device. In this case, will B device. You can ask a question here. Is it like, let's say you have partitionable system, and you have A and B devices, but let's say you still talking about the same system, but someone brings you another pair of devices, C and D, let's say, and you can, are those two partitions the same? That would be cool if, but it's not guaranteed in this formulation, right? We cannot guarantee that it's the partition into C and D would be the same as partition into A and B. Would have to.
Doesn't have to.
Yeah, you don't. Yeah, yeah.
It's not guaranteed that it covers the whole system. It's A and C.
Yeah.
You can bring the device C and it's still committed.
Yeah, I mean, maybe this actually is
nice.
third and fourth part. Who knows? I mean, you could think about it more if you want, and probably would be very.
What we can say about this knowledge.
First, you have to really think about it. Maybe you can actually say a lot. Let me one more observation, and we go to break. So the break is over. At least first break. Right. So we have our partitionable. We kind of understand what partitioning means, and now we want to build on it, because now I want to have independent systems, partitionable into independent systems. So,
but the subsystem.
like subsystems that are independent. So we have another observation about that. So observation when obs number 6. And it's how do I call it? Simultaneous measurements of independent systems. Simultaneous measurements. Independent. And well, we know that the example of Moon and Saturn, the systems are independent, right? But we have to confirm it experimentally that it actually makes sense, because who knows? Maybe the real world is so non-local that everything is connected with everything, right? That would be disturbing, right? But we have to confirm it somehow. So the observations, once we know about, we have the idea about partitioning. So it's kind of just, the wording is a weird. So the observation is that certain systems are found to be partitionable into independent systems. Subsystems. Subsystems. Trivial example would be like Moon and Saturn, right?
In the sense that some of them can be found.
So let us clarify this, okay? Because this is like, we want to have the word independent. let's clarify it. The constituent subsystems, so systems of a partitionable part will be partitionable, okay? System shall be, Davide likes shells, so there should be some shells in the text, shall be considered as independent and then when the results of the measurement of any subsystem observable. So subsystem, as a part of the definition of partitionable, right? I talk about attributing, observables to subsystems. So in this sense, subsystem observable in the sense of this attribution of any subsystem are indistinguishable from measurements of the same observable of the same obs performed when the measured, it's legalistic lingo, but and the measured subsystem is the only present system. So in other words, you have to compare. You have your partitionable system that you can partition into two bits or many bits, and you have somewhere different laboratory that have only those bits present. Okay, and you can so that you can compare measurements done on your partitionable system versus measurements done on your isolated systems, right? And you want to compare the results of those, right? This is how else, right? Again, we have very little info on our hands. We have only measuring devices, right? So in terms of, so now we can write it down, because these were words, but now we can write it down in terms of probabilities, in terms of probability distributions. Probability distributions. A and B are independent. When and now formula A, B, T. I will explain the notation in a second, although it's probably very, will be intuitive for you. So this is like a wedge symbol, like in end. Right? So this equals PA And of course, you expected that, there's some factorizations, right?
And then we are still in this picture of sequential measurements.
Of course, all the time. That's where, now let me the symbols, right? Where AJ wedge BJ indicate that A device and B device and AB device for short, right? And B device short. Okay, sorry. Were deployed simultaneously. Okay, you were deployed simultaneously. Sorry, I missed the line. So when A and B are deployed simultaneously, we say we deploy AB device. Okay, that's at time TJ and PAB is prob list. Of course, you can always refer to the PDF if you want to full text describing measurement with A or B device in an experiment where only one subsystem is present. Right, so this is what I said, that you have to have different experiments, right? To one experiment when there is only this A subsystem present, no B subsystem, so you can get your PA probabilities. You have to have experiment with B, and a third experiment when the AB are composed together, right? So, and they're independent. So the example with two laboratories, right?
And it's not results. It's not A.
No, it's just what device spits out, right? So it has its own display. A has its own display. B has its own display, and and this just tells us that the pair of results. So this wedge is like you can treat it as a two tuple, right?
In these devices, can be different, can be the same.
Yeah, both. We will partitioning into two copies of the same systems it's a very good idea to do, and we will do it at some point to figure out some stuff. But it can be whatever. It's just we have our idea of partitioning, and and now we have our idea of independence. And the key thing is that the factorization rule comes up, right? Because if you have some description in terms of probabilities, or other distributions, not necessarily probability distributions, but distributions, and you don't have this notion of factorization when things are independent, then you are in trouble. Because this factorization allows you to eliminate things that are unrelated, right? Through some integration, something like that. So if you lose factorization, local factorization, then you are forced to basically, when you describe anything, any bit, you have to describe everything at the same time, right? And that would just, no formalism can be, no sensible description can be made. So factorization rule is important, okay?
So this A divided by B?
No, it's A or B. Okay.
Okay, it's A or B. Oh, okay,
because it's not divided.
Okay, because I thought that you introduced the A except
No.
B or something like
No,
this.
Okay, so now let's carry on, because I really want to, I would like to finish this section because we are kind of so okay, we have independent systems, right? And now independent, we are told here that probability is factorized, so we need probabilities of A, probability of B. Those can be explained using if A and B devices were coarse grain or something, you have some interference, but in A and B independently, then of course interference term I, this function I, would be good to describe those interference experiments, this kind of interference experiments, right? But maybe, is it like, so now the question is, are those functions I for A, I for B, and products of them is enough to describe all interference experiments, okay? Because we in previous lecture, we introduced I's to do just that for when there's only one system, right? We explained everything. Now we have independent systems. We have this factorization rule, right? Which basically means that you can describe what's going on in A and B by describing what's going in A and B independently, right? That's the idea. So it should be possible to, so it means that I can describe what's going on in there using their local interference terms as well, right? Local. Yes, so some product of IA and IB, right? Should be okay. And now the question is does this cover all possible interference experiments we can do on this partitionable system where subsystems are independent, right? This is like a trick question. Can we figure out some kind of coarse graining that's like goes across those subsystems that will, introduce something new we haven't seen before? And there is this kind of interference, even if systems are independent, because you can have your A device, B device, but it's possible to imagine, and I will give you example in a second, device that is it's essentially A B bar device, which is not to be confused with A bar B bar device, right? Because this is like you do some coarse graining on B and coarse graining on A, but independently. So this would give you factorization, right? But this guy is something else. It's like you measure A and B, but this device has some trouble with making which subsystem distinction. Okay, so measures some observables, but it doesn't know from where it came from. So it's like classic Hamburg-Brown-Twiss experiment, right? You have photons coming from one part, photons coming from the other part. You do some, some stuff going on, and you do measurements, but you don't know. You measure some property of photon, but you don't know where the photon came from, and this causes certain kind of interference, right? And we want to focus on that. And again, this distinction, right? This versus this, those are very different things, okay? So once you accept that this kind of device exists, somehow. You know, Hamburger twist. It's an example. Then we have another. So we can now deploy it. Okay, we have our. Yes. Yeah. That's. I mean, I don't know at this point if I associate some. I mean, if there is a distinction between device and observable. We don't have enough information to make this judgment right now.
Yes, I want to say that on the left device, you need to measure something different than on the right hand side.
Yes.
Mm.
Yes. Definitely. I mean, this is what we talked about last time, that this quantum coarse graining, not this fake coarse graining, it requires that device does some physically different process, right? It's not like, so it's really, it's
not post-cross-grain.
Yeah, it's not post-processing. There has to be some different physical process underneath, yeah. Which is very quantum, right? It's non-classical thing. Okay, so next observation. Yeah, let's Penobs number 7. Quantum interference. Interference between independent systems. In the independent system. You know what? I won't be writing now because I would waste too much time. So we given AB device. Again, I refer to the PDF for exact wording. I will be saying it instead of writing. So coarse-grained device, so we have to provide its resolution to define it, okay? So we have resolution of AB bar with respect to AB fine-grained, okay? So this will be, as usual, this is basically to introduce notation, okay? So we have our small omegas, so those bins, right, for coarse graining. So this will symbolize the result. What is this of AB bar, right? So it's not, don't think of it as a like.
It's like,
yeah, it's A wedge B is a symbol here. It's a whole symbol. Don't. Which is some subset of omega A times omega B, right? Because those are something displayed by A, something by B, such that, and you know, we have the standard affair. You sum over, you take a union over all the whole spectrum of AB bar of omegas AB, and this gives you times omega AB, and they are not overlapping. So omega bar prime is empty set, okay? And now when you deploy this AB bar device in place of AB device, you observe interference, which we can quantify by writing when AB bar is deployed in place of AB, we get, if there is interference, this means that the interference term so we deploy it at some time tj, okay? So it would have a plus j bj plus minus Vj minus, which is interference term. You can express it in terms of probabilities. Again, this is this pairwise decomposition we were talking about last time. Aj and Bj plus pairwise. So wedge and V, we are stretching our notation to breaking point, essentially, right? But it's I think this is the most elegant way to write it anyway. So this minus the AB so those kind of formulas we had them last time, right? So I'm just recalling them. Minus Vj minus, and our systems are independent, so I can these guys they factorize. Okay, this I can write as PA, right? A minus times B, and so on. Okay, but the point we have interference, which means that this guy here, okay, is not zero. This means that there is interference. No interference would, yeah. That, in formulas, this is what we are saying. So this is the first part of the observation, and now here is the run. However, even though AB are independent, okay, this interference cannot be fully explained exclusively in terms of subsystem interference terms. Okay, so in formal terms, we can introduce something that I will call co-interference term. So this is co-interference term, and it will use the same conventions as normal interference term. And it is defined as I AB Tj minus the factorized interference terms. Okay, so I Ij minus times IB okay. So we take the interference term of our this interference term, and we check maybe it factorizes, and this thing in general is not zero. Okay. Yeah, if I could explain everything in terms of i's, this would be zero always, right? But it's most likely not zero. So we have a wrinkle. I is insufficient here, and it's to make matters worse. Okay, this is threatening us that maybe the factorization rule is also broken, right? Because we have this phi, which is some blob that depends on A and B, even though A and B are independent, and the simple factorization didn't fix it, right? So, oops, maybe we just lost factorization, which would be catastrophic, as I said, because then if you don't have independent systems, you don't have this factorization for independent systems, you don't have a means to define isolated systems. So we would have to describe whole universe at the same time, every time. And that would be just, that, I mean, it just wouldn't work. Nothing would work then. Okay, so we did our new version, new coarse graining, that which subsystem distinction is lost. There is interference because of that, and this interference is not explainable with interference terms alone. Okay. Next observation, the last observation here. I'm sorry if this is kind of rushed, but at this point, I think it's kind of clear what's going on. So we are very worried about this factorization rule. Okay, can we do some kind of experiment to figure out if it's still in place? Okay, and this is
Which checking?
Yeah. So something that could check if we lost factorization, maybe we are saved and still in place. And this is where we have to think about it, give it a think. And this is where the idea of taking, okay, nothing stops me from taking this partitionable system that is made out of two copies of the same system, of identical system. Okay, so I have two parts, but the two parts are the same. Okay, and then.
But then from where you can know that it is not just one? Why do you say that there are two parts, the same parts? Maybe
You can measure one, you can measure the other.
You can, I mean, you can, of course, you can never prove anything, right? But you can have a very good idea that you are okay. You make a lot of experiments. You measure it from many different angles, done all the. Besides, I mean, we are preparing your system in some way in your laboratory, right? So you might have some clues that it's reasonable to assume that I really have. There are two parts, and those two copies are. The two parts are the same. Okay, let's not be too annoying about that. I think it's reasonable to say that you can do it. Although maybe it's a room to have some discussion.
You know that there are two copies.
Yeah, we have good high probability that we know what we are doing here. Although it might be some very interesting vector for discussion. I just don't have any clever thing to say about this. I just, let's hope it works. So we want to check this, and here how using this idea that you have this kind of thing, you can actually make a test. Okay. So we have another phenobs. So we are spitting them out, right? One after the other. So this is interference between identical, independent systems. Again, there is some, we are considering this coarse grain. So we are considering this kind of coarse grain device. Again, full text is in the. So you take a identical system, so I can measure my observable f in one part, in the other, and I can consider the coarse grain version of it. This is the thing that triggers this new kind of interference. And we can, of course, set this f to be A or B, depending on our whims and setups. So we have this kind of setup. So we have, so let's say we have those, in one laboratory, we have AB composition. In other, we have AA, and we have BB, okay? So we can get a co-interference term from each one of those guys, okay? So we have, so we take phi AB, and we take phi AA, and we take phi BB, okay? And we want to compare them, right? So when you compare them, you notice the following relation. This is what you find by doing your experiments. You take modulus. This phi can be, it's a real number, but it can be positive, negative, who knows, right? To take modulus of AB, okay, plus EJ plus AJ minus J minus, it is modulus, and you find that it equals modulus phi AA TJ AJ plus and AJ plus AJ minus and AJ minus square root. So, it's positive or negative, so you have to, that's why you have to modulus. Or square root wouldn't make sense. Times phi BB J plus BJ plus minus, sorry. Minus BJ minus. And square root, okay. It's easier in tech. And this shows you that, so phi AB is a product of something that is only dependent on A, specifically square root of phi AA, and times square root of phi BB, right? So this means, if you agree with me, this means that the factorization rule is not violated here. We are retaining, okay? Because if factorization rule works, then phi AA, phi BB would be a product with a square of something. Something like only A times only A, but because it's an identical system, it should be symmetric, so it's a square.
Yes.
So you take a square root of this, so it's like gives you this A bit only, right? You do same with B, and this relation shows you that something like that happens with phi AB. So phi AB is a product of something of A and something of B, right? Otherwise, this decomposition wouldn't work. And there is more. There's second part, because there's interesting thing that happens. So this saves the factorization rule for us, but we can get even more interesting observations, because now let's focus on phi FF, okay? So we observe the following thing. You take phi FF, so A or B, whatever, just two copies, J, and you take Fj plus J plus Fj minus Fj minus. And on one hand, you can, so this should be a square of something, right? Because it factorizes and it's two copies, so it should be symmetric, and so it should be square. But you find that this guy is less than 0. It's negative.
So could you remind me this connection, this FF? What was this FF?
It's like a placeholder for AA or BB. Just you take.
So they are the same, yes. Step and that. Times the same thing. Yes.
Yes. So it's like a AA, BB. It's just FF general, yeah. So you just take your two independent identical subsystems and you measure the same observables at the same time. And there, if you do cross graining, you get this point interference term. should be, because we just saw that it factorizes from symmetry, we know, so this should be this phi ff should be a square of something, but the square is negative. So this something is purely imaginary. That's pretty fun that we can get it out of this. And we can get an additional thing. You can show that this the thing, this purely imaginary thing, is also anti-symmetric, because you get that this equals to minus phi ff and phi minus plus. So you reverse sequences in the one of the bits, and this gives you a minus sign. Okay, so we know it's purely imaginary, product of purely imaginary things, and those things are functions of two sequences, but anti-symmetric. So yeah, and so that's a bit of we saved factorization rule. That's very important for us. Okay, but we also have some clues where to go next, because in last time we got our we introduced parametrization with i's. Now we know I is not sufficient, but okay, so how to extend this? Because there is something good in I, because it already allowed us to explain a lot of things. So probably you have to add something to it to make it complete, get full parametrization as we need it. And this last observation basically like narrows down what form of parametrization we need. And like the easiest thing you can come up with, at least I think it's the easiest. And later we'll discuss more philosophical standpoint why it is easiest, because you have to explain from this, because I mean, yeah, it will be complex. So, but because we are it is a parametrization, but we are introducing some non-phenomenological things here, right? We are postulating some formal elements ad hoc, essentially, right? We will have to explain ourselves from that, right? Because we are deducing from phenomenology. Doing things like that, you have to have some good arguments why you do this, not something else. And there will be whole lecture about that, okay? But at the moment, we just want to have efficient way to see factorization and to, have this nice decomposition where we can consume all the coarse grain. So the thing, the extension to I is so we will introduce functions Q, okay? The same kind of indexing as with I. They will be functions of pairs of sequences. This cannot be, this is essential because of pairwise, right? But complex numbers, okay? Not real complex numbers. So it's kind of sequence pair distribution, not definitely not probability distribution, say complex number, but still some kind of distribution. And it has a couple of properties. We demand that it's Hermitian. So it's like if you take Fn minus Fn plus equals complex conjugate. Fn plus Fn minus complex conjugate, okay? So I was symmetric, this one is complex conjugate. It has this additivity with respect to coarse graining. Of course, it has to have this. This is the main point why we are introducing it. Coarse grained. So we have V Fn, right, to the full power of our notation on display. and it breaks down into Q of non-bar F, non-fine-grained F. Oh, some plus minus over omegas, right? Boom, Fn plus and minus, click. And next thing, the real part will be I, okay? So, how do I write it? IF. I mean, this is actually the most simple thing you can do. I mean, I already worked, right? It has to be incorporated here. So this is a very simple way to do it. Real part of Q, which immediately tells us that the real part is symmetric. So the imaginary part has to be anti-symmetric if you want Hermicity. And the imaginary part is it's fixed by the factorization of co-interference term, essentially. Co-interference term has to be a product of purely imaginary things, right? Let's take imaginary part of Q to be those things, times I. So phi AB J I want this guy to be simply given by I times imaginary part of Q, QA. Times I. So this square, so square is negative, okay? So this is how we comply with the observation 8. Bg minus. Okay, and now, so these are rules for our Q, and now we can do simple calculations to show that it works, like last time. And 10 minutes, I'm tempted to just bring up the PDF and just show what. No, let's persevere, because this is actually the last bit, and maybe we'll manage. Because yeah, so on one hand, we take our this which subsystem coarse graining. So we write down P A B T J. We have some A B, some coarse graining here. All right. And now we know, okay, so this guy can be expressed in terms of interference term. This is the rules from the previous. We did Q, we added some stuff, but we still have to be compatible with what we did previously. I is still valid parametrization, right? So they have to click in together, right? To make sure that we are not making any mistakes. So this will be diagonal part. And this omega, I will just shorthand, okay? I don't want to spend too much time writing everything down. So we are here. Now we can do use this additivity of this I to turn it into pairwise guys. And then once we do that, we can definition of co-interference term, right? It's a co-interference term is IAB minus factorized guys, right? So IAB is phi plus factorized guys. I just move it to the left-hand side, right? Because I want to have I want to have explicitly phi in my formula. So I take, first I do the additivity. So I have sum over I squares in omega. And I use what I just said. AJ plus AJ minus times, sorry, not AB, BJ plus BJ minus plus co-interference. Now I can use my rules for Q. So I can express I as a real part of Q and this phi AB as a product of minus product of imaginary parts because I imaginary unit squared. So this gives me sum and I have real part of QA times real part of QB minus imaginary part of QA, imaginary part of QB. Okay, so all the arguments as they should be. But this thing is a real part of QA times QB. Okay, the product of two complex real parts is exactly this. So this is on one hand side. So this is we have factorization we wanted, but you can go from the other side. Since the real part of Q is symmetric, imaginary part is anti-symmetric, so you take diagonal part of Q, the imaginary part goes away, all right? Because it's anti-symmetric. It has to, diagonal part must be 0. So you take Q, you take Q F, FF, it's equal to real part of QFF, but that's I, FF, because real part is I,
Yes.
which is P, F.
Yes.
Okay, so we can express through QP.
Okay.
Yeah, with a real part is gives us P. So we can do, so we take our probability that we started the previous calculation with, V omega and we write it as a Q AB that is V A plus B A plus V omega minus B A minus. But we have additivity, right? So we have sum over omega, and we have Q AB. So we consume coarse graining here. And we sum over all the pairs, plus minus B, plus minus, right? But look, for every term that you have some A plus, B plus, A minus, B minus, you have also the reverse, right? So this sum symmetrizes everything. So imaginary part is anti-symmetric, so this sum just eliminates. You are left with real part of QAB. We're almost done. We're almost there. Last thing. So we have the sum over omega, a real part, according to what I said. AB, J. So we have sum over real part of QAB, and here we have a sum of the same sum of a real part of the product, which means that QAB for independent systems factorizes into QA times QB, which is what we wanted to achieve. So it implies that QAB, we can even write it as a in our tuple notation. AN plus BN plus AN minus BN minus for independent A and B. It's a product of QA times QB. Works. We have a factorization, and at the same time we are dealing with interference, even this weird witch subsystem interference, because we have, we can consume all the bars by turning them into sum over Qs that don't have bars anymore. So it's like and it has a pairwise in it because it's two sequences, and it works just fine for one system scenario because of this symmetrizations and stuff like that. Only the real part actually takes any role has, right? So we are consistent with what we did before, and we are and most importantly we have factorization still. So nothing is non-locality, whole universe doesn't have to be involved. And so it was kind of formal stuff, but I just want to reiterate how much we had to do, just this partitionable, this super interesting, right? And to like figure out that this imaginary part is there. There's experiments with same copies of systems. This is like, that was so much fun figuring this out. Because in advance, a year ago or 2 years ago, we knew that there is this imaginary part, but we just couldn't find it. We thought that you have to just assume that it's there. But then we figure out that there are actually independent, you take in two independent systems, the imaginary part comes up. This is like, we're inspired by works of Dioshi, who actually was talking some time ago on CFT seminar. It's like some guy, gravity and stuff like that. He also wrote a couple of interesting papers where he used this trick of two independent systems to get something. Look, if there was only one system, everything is explained by this I, the real part of Q, in other words. You already know that you will get Q. And there is nothing you can do there is no measurement that would reveal you the imaginary part. Everything is just symmetrizes all the time. So, but as it happens, this symmetrization, because you have two systems, you still have symmetrization, but now you're symmetrizing product. And this can become sensitive to imaginary part. It's like, I don't know what's the deep story about that, but this is, the lesson from this is that when you are doing some fundamental thinking, deducing stuff, you should always test you take your system, do some stuff with system, test dynamics, test some structural stuff, whatever, but then also do similar stuff for many systems that are independent. It most likely will reveal something that single system cannot. So this is like general, if you are doing some fundamental stuff, keep it in your pocket, okay, this trick. And so this concludes our, the first part of phenomenological stuff where we are like sussing out the structural things about our, theory we are examining. The next lecture will go through the second part of phenomenology where we probe dynamics, okay? Because now we have structure, we can go from here very far already, but the next part will be to how this stuff, how is time involved in this? And those two things we smash together, and this will give us a fuel for our deduction, which everything go from there. So yeah, so 2 hours. We can finish it now. So I'm